So we have, like I said, distributed systems. These are a set of machines that are connected over the network. It might be a set of virtual machine connected over the network, containers, and so on. And the question comes down to how can you make collective use of these multiple machines, right? And that's where we get into how do you make it easy to program distributed systems, right? Because if you think about it, if you had to have even two applications talk to each other on two different machines, how would you do that? You essentially have to write maybe a client, you'd have to write a server, you have to open a socket, you have to agree on how, what protocol or what way you would be sending data to one from a client to a service, how it would respond back to you. And now you have to do this for many machines, right? And then you'll have to figure out how do you take a larger application and decompose it into smaller services or microservices that you want to execute and so on. So decomposing an application into a form that can make use of multiple machines is not easy, right? It can be fairly challenging. And it requires a lot of coordination, synchronization, data and message passing, and so on that happens between the various component tasks of an application. And you also can get, if you're not programming things properly, you can get into things like deadlocks and race conditions and so on, which goes down to even how do you even design a distributed application so that it behaves correctly, not from a not suffer from just a coding bug, but just a conceptual bug, just in the way you are interacting with things, right? And like I said before, just less like C++ is a higher level language that compiles your code into assembly. You would also have things like MATLAB or other forms of even higher level languages that behind the scenes might actually make use of C++ libraries, right? Which in turn get executed on assembly and so on. So there are different levels of abstraction that you yourself have dealt with on a daily basis, right? So now the question is, what is this kind of higher level programming language that on which you can write your application, and behind the scenes it can actually run on multiple machines with you not having to do all the heavy lifting or complexity of having to interface between many of these machines, right? That's really where distributed platforms come into play. And it's not just that these, you have to sort of coordinate among a lot of machines, right? So the moment you have many machines, a lot of things that were uncommon on a single machine start becoming more probable as you increase the number of machines, right? Things like failures, right? So while it's maybe rare for a single server to fail, the moment you're running 10 servers, the chance that one of them will fail goes up by 10 times. When running under 100 servers, the chance that one of them will die or fail will go up by 100 times, right? And if these are machines that are sort of running 24/7, like a cloud data center might be running, with a lot of stress on the system, it's not like it's idle all the time. Most often it is actually doing something up and running. Then the chances of failure are much higher, and you have to ensure that if something fails, you don't have to completely restart the application and lose everything that you've been running for the past minutes or hours or days, right? So if you remember, in clouds, you're paying by the minute or by the hour, right? So let's say you sort of rented 20 VMs and you're running a job for an hour, right? And at the end of the hour, before your job completes, one of the VMs fail. And you don't have a good means, your platform didn't give you a good means for recovering from where you left off. It essentially means that those 20 into 1, that's 20 VM hours of money that you paid has just gotten wasted, right? So it's not just productivity and time that you lose. You can actually lose real money if you are running distributed applications on the cloud and those application platforms that you design or you use don't come with good recovery and resiliency features, right? So now let's get down into specifics on what we talk about these mysterious platforms as a service, right? One of the essentially almost like the pioneers in big data platforms, right? So came out of Google. This was in the early 2000s, and this was a platform. It was more like a programming language or a programming model called MapReduce, right? And Google, in a sense, invented this programming model because in the early 2000s, as they were hiring people, right, hiring developers, they realized that most people couldn't do good distributed programs, right? Because it was not taught in your courses, right? So it was not a common thing. And even today, how many of you have done distributed programming? Just maybe one or two, right? So even today, 20 years after the distributed programming became mainstream, right? We still don't have enough skill sets for writing or developing distributed applications, right? And Google effectively was a company that did everything distributed because they have to scale to a lot of users, right? So when we talk about weak scaling earlier on, if a single Google server could handle maybe 10,000 users, right? You really want them to be able to weakly scale. So you got 20,000 users, you want to add one more server, right? You got 40,000 users, add 4 servers, right? And so on, right? That's an example of weak scaling. So many of the things that Google builds or many internet companies build, or nowadays most even e-commerce sites build, they are designed to weakly scale because you have to scale with the number of users that you have, number of transactions that they perform, right? Which meant that Google, just to support their search requirements, required a distributed programming language so that their developers could easily write distributed programs without having to go through a steep learning curve, right? And in fact, one of the biggest workloads that Google had, which is one of the reasons for them to design this MapReduce programming model, was the actual indexing of the web once you have crawled it, right? Because when you want to build a search engine, as Google was building 20 years back, the first thing you want is data. You go acquire data. And like I said, the way to acquire data from the web is to go and run a BFS, right? Start with the website, go to its links, download those websites, go to their links, and so on, right? That's pretty much what a web crawler does, right? And once Google has crawled all these web pages, you got a bunch of these, let's say, HTML files sitting around, bunch of these text lying around. Now you have to index this, right? And you got various indexing techniques. You can do an inverted index from a keyword to all the URLs having those keywords and so on. So that's one part of the problem, right? So how do you go from a large set of documents to an inverted index that goes from a word present in those documents to the URLs that have that word, right? Because when you're doing a search on the web, you want to give a keyword and you want to get a list of URLs that match those keywords, right? That's step one, right? But if you did a Google search, how many hits do you typically get? Has anyone sort of looked at how many of those 1, 2, 3, 4, whatever numbers are there at the bottom? Often it's going to be 10, let's say. It's going to be more, right? Unless it's a very, very specialized search. It's very likely that Google will keep giving you many, many URLs, thousands of URLs potentially that have that keyword, right? So let's say it gave it to you, but do you actually end up going through all those thousands of URLs, right? You don't even notice the things on the bottom because very likely what you want is in the first few hits, or at least in the first page, like your first 10 or 20 hits, right? Which means that it's not just indexing that's good enough, where you actually return the URLs that match a keyword. You also need to rank these URLs, right? Let's say you got 1,000 URLs that have a particular keyword. Giving this 1,000 as a set is useless. What you need to do is give this 1,000 as a sorted list, such that at the top of the list you have the web pages that are most relevant to that particular search, right? That's why Google, when you do a Google search, you rarely need to go beyond the first page because Google has sort of mastered this trick of if you're searching for something, it knows very likely what is going to be the most relevant URL for you, right? So that means that you have to come up with some kind of a ranking strategy for these URLs. And back then when Google started, they started off this algorithm called PageRank, right? That's sort of one of the reasons Google became so sort of popular as a search engine, because the PageRank algorithm they came up with was very effective. When people did a search, they actually got very useful results, right? And that is actually a graph algorithm, right? It's actually a graph traversal algorithm, it's a random walk algorithm. That is going to be running on what we saw right now was more than 1 billion pages, right? You've got a graph with 1 billion vertices. The links are the edges between the web pages. So if page A has a link to page B, page A and B are vertices, and there's an edge going from page A to page B, a directed edge, right? So when you run the PageRank algorithm on top of this large graph, what you end up with is essentially a ranking of all the vertices, saying that hey, these vertices are very important because many people link to this particular web page, and these pages are less important because not many people are pointing to that web page, right? So on something like Twitter, does it matter if you have a larger follower or a larger followee list? You really want to have people who are important have a lot of followers, right? On the other hand, if you follow 10,000 people, are you important? Not really, right? You just have a lot of time in your hands, right? So what matters is the number of links that you have coming in to a web page. That tells you how important that page is, right? And PageRank essentially makes use of this concept as from a graph algorithm. So now Google has these two problems, right? You have to index the web pages, and you have to build a ranking of the web pages, right? The first is a text mining problem. The second is a graph analysis problem, right? And they said, hey, we want these to be distributed because we could keep tuning these algorithms very frequently on a weekly basis as to improve things. So we want to sort of design these using a distributed programming model such that I can do everything from text mining to graph processing using the same programming model, right? It has to be very versatile, right? But at the same time, it has to scale, right? If I write it, today I might give it 10,000 pages, tomorrow I might give it 1 billion pages. It should weekly scale, meaning that if I can run 10,000 pages of indexing on a single machine in 10 minutes, I should be able to run 1 billion pages on the equivalent scaled more number of machines and still get it done in 10 minutes, right? Because my pages are going to keep increasing. The time that I have to index is not going to keep increasing, but I can throw more machines at it, right? So that's sort of the genesis for, in a sense, big data as we come to know of it, right? So if Amazon and their e-commerce site and their spare capacities that they had in their data center was the genesis for cloud computing as we know of it today, Google with their web crawls and their need to index it and build ranking on top of it, on top of distributed systems, on top of their private cloud, was the genesis for big data platforms, right? So, and both of these happened in the early 2000s, coincidentally at the same time, right? So we'll talk about, so MapReduce is two things. So one is the programming model, right? Just like you have C++ as a programming model, and then you have various C++ compilers, right? You got your GCC, you got your CC, you might have your Intel compiler and so on. All of them can take the same C++ compiler, but compile them to different architectures, right? Compile them to different systems that you might have, right? Likewise, MapReduce itself is a programming model, but at the same time you have runtimes for MapReduce that will take a program written in MapReduce, or at least in the MapReduce specification, and it will run it on different types of distributed systems. It might even run it on parallel systems on a single machine, right? So that's the distinction between MapReduce, the programming model, and Hadoop, which is one of the open source implementations of the MapReduce platform or the MapReduce runtime. So it can take a MapReduce application or an application written in MapReduce and can run it on top of a set of distributed machines, right? And the other thing that we'll talk about is Spark, which is another runtime for MapReduce, but it actually expands the MapReduce language, right, to be something even more sophisticated or easy to write. But at the end of the day, it's almost like a layer on top of MapReduce, because any of the programs that you write in Spark effectively can be compiled into a set of MapReduce applications. And those MapReduce applications themselves can be run on top of Hadoop or the Spark runtime, right? So in a sense, if you think about it from a layering perspective, like your MapReduce code runs on top of MapReduce runtimes like Hadoop and others, and your Spark is like a higher level language abstraction on top of MapReduce that allows you to run things on top of Hadoop or Spark runtimes, or MapReduce runtimes like Hadoop or Spark, right? So one of the other concepts, if you won't get into that in detail, is in terms of the distributed file system, right? Google file system or Hadoop distributed file system. And when Google came out with their MapReduce programming model, they simultaneously also came out with a distributed file system, right? And the reasoning was this, right? So if you have a number of machines, and if you don't know how many machines you're going to have, you don't know what the workload is going to be, right? And it has to be elastic, as in today you might have 10, tomorrow you might have 200, and tomorrow you might have 1. if you had a very centralized file system, right? There's one file server and everyone goes and talks to that if they want to get the data, right? So which means that if you have one VM, great. If you have 200 VMs, you might be in trouble. So your performance is going to vary dramatically, right? So what Google said when they came up with the MapReduce is that our file system will be distributed as well, right? And what we'll do is that the same machines that run our computation will also hold parts of our large file, the entire web, let's say, right? So you don't have the separation between a set of machines that do computation and a set of machines that are just used to serve files. Both are together on the same set of machines, right? So the same machines that store your data or parts of your data will also perform computation. And hopefully the MapReduce runtime will be smart enough to say that if this part of the application is working on so-and-so data, I'll run that part of the application on that particular machine holding the data, right? It's not like I'll run it on some arbitrary machine and pull the data from a remote machine to me, right? So you want to actually push your computation, you want to push your application to the data rather than pull the data to the application, right? So if you think about it, how large do you think you guys watch movies, right? So how large do you think the binary of a video player is? A few MB, maybe tens of MB at most, right? How large is your movie file? Probably gigabytes in size, right? If you're doing HD and a 3-hour movie and all those things, right? So that's sort of typical application binaries are much smaller in size compared to the data that you're processing. And this goes for most things. Any non-trivial application you're going to write, your data is probably going to outstrip the size of your application, right? Which means if I had data and compute, or if I had data and my binary is sitting on two different machines, does it make more sense to send my binaries to the data or get my data to the binaries? It's probably sending if you did data to your binary, you're sending more over the network, right? You're sending movies are probably a bad example for that because it's not like you can send your movie player to Netflix and watch the movie inside the Netflix data center, right? So because you are physically consuming the output of the video player, right? But typically, you are going to, it's not an interactive application. Most applications, real applications in the world are not interactive applications, right? They're off running in the background, right? So you actually want to send your binaries to the data and have the binaries executed in the data, and maybe you just want to have the results given back to you, right? So if you are doing a Google search, you send a query to Google and the Google runs it locally there, right? They don't ship you the entire web crawl to you and say, hey, you figure it out, right? So the point is that you want to design, when you design these big data platforms, data is typically extremely large. The applications are much, much smaller in size. And you want the data to move as little as possible, right? And instead you want the binaries to move to where the data is present. And you want the binary to execute locally on the data as far as possible. You want to get the result out of that, which is hopefully much, much smaller than the original input data. And that can be something that's sent back to you, right? So that's another concept for you to keep in mind, which is why when they designed the MapReduce distributed programming language for big data processing, they also designed a distributed file system so that the two of them can work closely together, right? And the open source implementation of MapReduce is Hadoop and also Spark. And open source implementation of the Google file system is also called the Hadoop distributed file system. So here are a couple of maybe slightly dated software stacks or platform stacks, if you want to think of it in that way, right? So remember in one of the earlier lectures, we talked about the various layers of your IaaS, PaaS, and so on, right? This is almost like zooming into the PaaS layer and seeing what other fine-grained layerings could be within a platform as a service, right? So at the bottom over here, you can think of this, everything below this is IaaS, infrastructure as a service, right? And everything above this is software as a service. What you're seeing over here is one flavor of platform as a service, right? Because even within that, you got many, many layers, right? So this is an example, maybe from 5-6 years back, on how a Hadoop platform stack would look like, right? So at the bottom, you'd actually have a coordination layer that helps you coordinate across different machines, right? See if they are alive, if they are dead, if you want to sort of do some synchronization, some coordination. This would actually take care of talking across those different machines. Then you'd actually have the core Hadoop engine that actually runs a set of tasks in a coordinated manner where you can sort of write your language, write your Hadoop program in the Hadoop language or the MapReduce program over here, submit it to Hadoop, and it'll execute it, right? And you could also have other types of higher level languages on top of Hadoop, just like you have Spark that is popular now nowadays. You used to have languages like Pig and Hive, which are again higher level languages that were built on top of MapReduce, and it would get compiled to MapReduce jobs, which would in turn run on top of the Hadoop language, right? You might also have user interfaces that allow you to just drag and drop different tasks together, right? And compose it nicely visually. And behind the scenes, it automatically generates MapReduce code that you launch and so on, right? Likewise, you might have a bunch of these, you might have sort of scheduling engines that sort of figure out that, hey, if you have so many tasks and so many virtual machines, here's how you have to map tasks to virtual machines, right? Because that's the most efficient way of doing things, right? So this is how a platform stack might look like, with the infrastructure below you and the software that you develop sitting on top of that. And if you think of the Spark stack, right? Spark again has its own ecosystem of things that are layered above and below it. So here's the Spark engine. So this again is sort of your platform as a service. And over here you start looking at this as your infrastructure as a service. So that starts from this resource virtualization layer that you have over here, right? Because that's what you guys have been listening to in the last few days, right? So this virtualized resources are managed by Hadoop Yarn, which is sort of like a resource allocation manager, and that's sitting over here. And then you have your HDFS, which is almost like a storage as a service, right? It's again a platform as a service, but here you're thinking about, though it looks like a single file system, right? In fact, you'll be using HDFS in the afternoon session as part of a lab session. You have very simple commands that the equivalent of ls or put or copy and get and so on, right? All of this sounds seemingly like what you would do in your common shell, but behind the scenes, that actually gets executed in a distributed manner. So HDFS is essentially hiding a distributed file system and making it look like it's a single local file system, right? So that's why this platform hides the infrastructure complexity for you, right? And on top of this, you have Spark that's running. We'll sort of skip some of these additional storage abstractions over here. The Spark engine runs over here. And on top of that, the standard language is higher level language is Apache Spark, but you also have additional interfaces, which are more higher level than what Apache Spark language might give you, right? You might be doing specialized higher level languages for doing graph processing, right? Behind the scenes, whatever graphics language gives you will get converted into a Spark language. And internally, the Spark language itself will get converted to a bunch of MapReduce primitives. And that would actually be run on top of Spark, right? But Spark graphics gives you a more easier way of looking at data as linked data, as graphs, right? As adjacency lists and so on, right? Rather than think of it as a bunch of tuples or a bunch of CSV files which embody a linked data, right? Likewise, you might have a SQL-like interface for dealing with data. If you want to do the equivalent of a filter or some kind of a projection or so on top of semi-structured data or sort of columnar data, then you could write it in a higher level language, Spark SQL, and which looks similar to SQL, your database SQL, and that in turn will get compiled into the Spark language, which in turn will get converted into a bunch of MapReduce-like jobs, which in turn will get written to executed on Apache Spark, right? So whenever you're looking at these big data platforms, you might have a core engine like Spark or Hadoop or whatever else might come out later out there, but there's typically a bunch of layers on top of it that make it even more easier to express your applications in that particular core engine or the core language that it exposes, right? All right, let's, I'm just going to skip past this. So we'll spend the next about an hour or so looking at sort of the conceptual building blocks for Apache Spark, right? And we'll also get a little bit more into the language primitives that it offers. And the tutorial in the afternoon you'll actually do a hands-on deep dive into Spark and HDFS and try out your own programs as well, right? So again, there's a bunch of external resources that you can tap into as well, where you have much more detail that's available. All right, so there are two key reasons why you would use Spark, right? So one of them is you want to be able to easily write distributed programs, right? The ease of programming, right? So coming up with an idea for a program, to algorithm that can be expressed in Spark, to running it with automatic weak scaling on top of a set of machines, right? So that's one benefit. The other benefit is more in terms of how the Spark engine itself operates, right? So which is very different when it came out 5-6 years back. Spark tried to take a very different approach in terms of how you would process data, right? We just talked about moving your compute to the machine where the data is sitting, right? So that you don't have to, instead of shipping the big data over the network to where your binaries are, you want to ship the small binaries over the network to where the big data is present, right? And that's because your network is a very slow resource. Compared to your CPU, the network is much, much slower, right? But within your machine, is the hard disk slower or the RAM slower? Hard disk is way slower than the memory, right? Your main memory. So what Spark essentially said is that I won't just ship my binaries to where the machine is sitting, where the machine has the data. At the same time, I actually take the data that's sitting on disk and keep it in memory all the time. Or when my application is running, right? I'll keep it in memory, right? So your access to the data on that local machine is now going to be much, much faster because data is already in memory, right? And not on disk. So the time that it takes, the milliseconds or seconds that it takes to load the data from disk into memory goes away, right? And the seconds or potentially minutes that you might take for moving the big data to compute has already gone away, right? So these are the two key things that Spark gives you: a higher level programming language for designing weakly scaling data intensive applications, as well as a very efficient execution engine, right, or a runtime engine for executing these Spark data flows using in-memory computation. So just to give a flavor of what we mean by in-memory compute, so typically when you write a application, right, so that gets composed into a series of, if you write a Spark application, that gets composed into a series of MapReduce jobs, right? And the way your classic Hadoop MapReduce execution engine worked is each of these MapReduce jobs will actually read data from memory, read data from disk into memory, perform the particular MapReduce tasks, and write the output back into disk. Then the next MapReduce task in that pipeline will read the data back from disk into memory, process it, and write it back, right? Which meant that by the time you had finished writing a particular application from start to end, you would have read and written from disk probably a dozen times, right? And that is extremely slow, right? Another example could be, let's say you have sort of static data and you want to be running a lot of queries on top of that, right? So here again, if you kept all your data on disk and for each query that comes in, if you loaded the entire data from disk into memory and performed an operation, that's going to be slow, right? So in both these cases, whether it's a sequence of tasks that are reading and writing in a pipeline, or a single large data and a lot of small tasks that are independently processing that particular data or querying that particular data, in both these cases, you will benefit if this data didn't hit disk at all. Rather, maybe at the very beginning, you read it from disk into memory, but once you get the output from the first task, keep it in memory and let the next task operate on this data in memory, right? And so on till the end of the pipeline. Once you're done with your application, maybe write it back to disk, right? So that's sort of the high level idea with Spark, right? So when an application is executing, when you have, so think of it as almost like function calls from your main method, right? Every time you do a function call, let's say you had to hit disk, that's going to be much costlier. Let's say if you had, instead of passing variables, right? When you have a main method and you call a function, you pass an input parameter, you get an output parameter back, right? And you call a different function, maybe with the output of that. And that does another output back, right? So this is your typical application, a bunch of function calls that happen, right? Now let's say instead of passing these variables, right, you actually have to pass those content of those variables on disk, which meant if I had to call a function, I'll actually write the input variable onto a file, pass that file name to, and that function would actually read that file name, go to that file, read that parameter from the disk into memory, do the processing, write the output back to another file, and return the file name of the output back to the calling function. And now this will go back and read it from disk, right? So instead of these small functions we have, think of each function as a fairly complex Hadoop function, right? That's effectively what happens over here, right? So when you call a function, it reads it from disk, the input parameter, writes the output parameter to disk, and the next function goes, reads it back from disk into memory, and so on, right? And Spark essentially says that, nope, maybe the very first input I read from disk, but after that I pass in-memory references. But these are my references in distributed memory. That's sort of the analogy compared to your single machine functional programming that you have. Right? All right, so one of the key ideas behind Spark that makes it very easy and elegant to use is something called resilient distributed data set, right? How many of you here have used Java collections, like ArrayList, Map, and so on, right? How many of you have used standard template library, C++, right? Okay, how many of you have not used either of these, right? And this is not to put you in the spot, this is just to make sure that I establish context, right? So maybe some of you, okay. So the idea is both in STL and C++ as well as Java collections, the idea is that you have a collection of items, right, that you keep as part of a data structure. And depending on the type of the collection, right, whether it's an array or a queue or a stack, right, the order in which, or the types of operations that you can perform might be different, right, and the order in which you might access things might be different. So there's a set of contracts, there's a set of API that each of these collections allow you to do, right, like list, map, and queues are common examples of these, right. But at the end of the day, all of these expose an interface for you, right. And behind the scenes, there are multiple implementations for this interface, right. So you might have a queue interface, but there may be different implementations of a queue, right. There may be a priority queue, right. There may be a sort of other kinds of, maybe a concurrent queue, right, that supports multi-threading and so on, right. So what Spark did was that rather than think about it as a programming language, right, think about it as a library, right? Think about it as a data as a collection, right. Even if it's large data, even if it's terabytes of data, even if it's a billion rows of data that you have, think about it as a collection, right. In fact, think about it as almost like a set or an unordered list. That's a better way to put it, right. So all data in Spark is seen as an unordered list, right. And Spark allows you to, and this unordered list is called a resilient distributed data set, right. So resilient distributed data set is nothing but an unordered list of items. That's it, right. Now, just like if you have a list data structure in Java or Java collections or STL, it'll allow you to, let's say, get the first item, right. It might allow you to do a count, right. It might allow you to maybe search for an item, right. So these are all standard operations that collections allow you to do, right. Now Spark essentially said we'll do something similar, right. It might be a terabyte of data, it might be a billion rows, right. But think of it just as a unordered list, and I'll allow you to perform operations on top of the items present in the list. Right? And they essentially say that it's not just going to be just finding an item or counting the item. I'll allow you to do operations on top of the item, right. Essentially they're saying that I'll allow you to give me a function, and I'll apply that function on every item in that collection, right. And the output of the particular function which I'm applying on every item, I'll create a new collection out of that, right. Let's say you had a list of marks for all students in IAC. Maybe the semester is coming to an end. We have 10,000 students enrolled. You have their marks available to you, right. And recently IAC went from a grade point of 8 to a grade point of 10, right. And both these systems still coexist, right. I think at least for another year or two it will coexist. So let's say you want for, or maybe it's more than that because you got multiple courses, because that are available for various courses in a particular semester, and they are in an 8-point scale. And you want to convert them into a 10-point scale. This is actually a common thing that happens, right? Because depending on what year a student is enrolled, and you have to go between 8 and 10 point scale, right? Now, all you need to do is take this list of, let's say, 50,000 marks in the 8 point scale and multiply it by 8. And your job is done, right? And if you had to write a sort of simple Java or C++ code, given a list, you'll do an iterator over the list, right? Take every item, multiply it by the scaling factor, and put it in a new list. Job done, right? So this is a very simple piece of code, but let's say these were in 50,000 marks. Let's say these were 50 billion marks, right? But still, the same code will work, except that it's going to take forever, right? But the same code may not work because you don't have a machine that can store 50,000 records in memory, right? So maybe you have to load it from disk, the first chunk, do the conversion, write it back into disk, load the next chunk from disk, process it, write it back. And if you do this enough times for different types of operations, not just scaling and so on, you've started building a distributed platform, right? You started defining your programming language. It says, I want to transform an item and create a new item out of that, and that becomes a new collection, right? That's effectively what Spark is. So Spark allows you to take a collection, an unordered list, a collection of items, perform an operation on top of that. And this operation, there are certain semantics to the operation, we'll go through that. But all it says is that the operation is like a function. You take that function, you apply it to all the items in the RDD, items in the collection, and you'll get a new collection, which is the output of applying this function on that, right? So that's one of the key ideas over here. So I'm just going to skip past these. Now, so if this is all that Spark gives you, you could very well do this using your list or whatever STL or Java collection operators that's there, right? The key benefit of Spark is that it allows you to do this even though the data present in the collection is spread across different machines, right? Because what you see is just this RDD interface, just like you see a list interface or a queue interface. Behind the scenes, this list might have a billion items, and the billion items might not fit in the memory of a single machine, but Spark splits the data into different sub-collections and puts them on different machines, in memory on different machines, right? So which means that as long as the amount of total memory you have in all the machines in your cluster, right, is good enough to fit the data, good enough to fit your collection of items, you're okay, right? And even if you didn't have enough distributed memory to put all your collections, keep all your collections in memory, it can still sort of keep part of it in disk, load it when you're processing it, and write it back to disk, right? All of this is hidden from you. It's done automatically. All you care about is that you have this collection interface. You have a bunch of functions that are on top of that. You call those functions, and those functions will execute in a distributed manner, and they will weakly scale. Okay? That's a benefit that you get, right? So this RDD, which is like an unordered list, which is sitting in memory, which is sitting in distributed memory, right? That's why the term resilient distributed data set, right? The data set is because it's a collection. Collection is a type of data set, right? It's distributed because this collection is present on different machines. And third part is resilient, which gets into the recovery and other primitives that Spark and its execution engine gives you. We'll skip that for a moment. But if you look at, let's say, an example over here, the sub-collections that I talked about, RDD is like a collection of items, and the sub-collections could be in different machines. The sub-collections are also called partitions, right? So an RDD is, one way to look at it is a collection of items. Another way to look at it is that it's a set of partitions, and each partition itself is a collection of items, right? And each partition can be on a different machine, right? And whenever you perform an operation on RDD, it will create a new RDD for you, right? Meaning that Spark does not allow you to change an item in a collection. It only allows you to create a new collection out of it, right? Which means that you can't pass by reference, right? So in Java, C++, if you pass by reference, the function that gets it can modify it, right? And when the calling function sort of gets the call back, it'll actually be able to see the modified reference, right? Spark doesn't allow you to do. it's only pass by value, right? Which means you can pass the RDD. The RDD is there. You call a function on it. The output of that function will be a new RDD. It can't modify the current items in the collection, right? It's like a read collection will create a new collection or a new RDD, right? So let's look through a few examples just to put things in context. I think we are slightly at the abstract layer and probably losing you guys. So there are two types of operations that you perform on the RDD. You can perform on these collections, right? So one, like I said, you can apply a function. That function gets applied on all the items in the RDD, and it creates a new RDD, right, with the output of that operation. Another type of operation is called an action, right? An action is designed in a manner such that you'll perform an operation on this collection, and it will return some kind of a scalar. It won't return a collection back to you. It will return something that you can write to disk, right, or you can print to screen, right? An action is effectively the equivalent of a return statement. You're done with all your operations. Now you want to return the result back, right? And after that, you stop seeing it as a collection, right? So that's the difference between a transformation and an action. Transformation RDD dot transformation gives you a new RDD. For an action, it's RDD dot action gives you a local variable, right? Or gives you a scalar value, right? Or a single item. That's the way to think about it. So if you look at these transformations, these are all fairly intuitive. What do you think a filter is? I've got a collection of items. I pass filter to it. What do you think it should do? So it should reduce the number of items. So in a sense, it should, whatever condition that you pass in the filter, right? Items that match that condition, you'll want to keep it. Items that don't match the condition, you want to throw it away. It's like a select star from this RDD where tuple value equals 10, right? Or tuple value starts with foo. So all that will do is take the input collection, and all the items that start with foo will be present in the output collection, right? Things that aren't present, that don't match this, will not be present. That's it, as simple as that, right? A map is even simpler. It doesn't even do any filtering or reduction. So in a map, for every item that's present in input collection, it will perform some function. And whatever is the function's output, it will just be put in the output collection, right? So if I had to sort of do my grade point scaling from 8 to 10, I'll just take all my inputs in one RDD. I'll do that RDD dot map of, take that input, let's say the variable is x, return x into 10 by 8. That's it. So the input I pass to that map is going to be this function that says take and multiply x by 10 by 8, and that will create an output collection with the same number of items as the input collection. If the input collection had 10,000 marks, the output collection will also have 10,000 marks, except that this function would have been applied on a one-to-one basis, right? A union is even simpler. A union takes as an input parameter another collection or another RDD. You do an RDD1 dot union of RDD2, and you're going to get a new RDD which just has the union of these two items, right? One thing to be careful over here, this is not a set union, because in a set union, you would remove duplicates. This is not a set union, it's almost like a concatenation, set concatenation, or it's not even like, a set is not the right thing, it's like concatenating two lists, right? So you'll get a larger list with the number of items in the list going to be equal to the sum of the items in the two input lists, right? And you got other things as well. For example, a join is similar to your database join, right? So where you have two lists and you do a join of these two RDDs, and for this you need this notion of a key, because in a database we are doing a join, you do it on some specific primary key or a specific column that's present in both of them, right? So we'll get to some of these things, but point being that just by looking at the name of the transformation, you can guess what it's doing. And that's sort of the simplicity of the language, right? So it's not complicated at all. You can just combine a bunch of these things and come up with some interesting analytic that you want to solve with the guarantee that it will scale to potentially billions of items. That's really the power that you get, though the language itself looks very simple. Right? How many operators does SQL have? Or how many sort of primitives or sort of keywords do you have? Object, join, aggregate. Right? You can have a bunch of UDFs and all those things. 4 things, right? But using this, people sort of like immensely complicated pieces of enterprise code just using SQL. A return, it's like sort of select star from select into X from my table, and that's it. Right? Filter is like your where clause, right? Your join is like your database join. We'll get into that, right? Some of these actions and some of these group by aggregate operations. Right? So again, a count. Count is again fairly intuitive. It just returns a count of the items in the RDB, right? And since you know that the count is only going to return a single value, it doesn't make sense to put it in a separate RDD, right? You do a RDD.count, you get a single scalar value, you're done, right? So that's the end of your program, right? Set RDD to disk so that you can go on and later on scale back into memory as an RDD and start processing that, right? All right, let's go through maybe 1 or 2 examples before we wrap up. And like I said, in the lab session, Sriram will cover way more detail, and you'll actually get to do some of these things hands-on as well, right? In fact, this is one of the data sets you will be using in the lab session, and this is a data set called Movie Lens, and it has a collection of CSV files, right? So the files, one of the files is called movies.csv, and it's got a few thousand rows, maybe tens of thousands of rows, where each row has the ID of the movie from IMDb, the title of the movie, and the list of genres that that movie is classified under, right? So this is a multi-valued column, right? And let's say I just wanted to do a simple Spark program on top of this CSV file, right? First thing I do is SC is short form for Spark context. It's like an initialization. It's like an initialization step that you go through to create the Spark context. Like you might give it the name of your cluster, the number of machines that you have, your username, password, stuff like that, right? So that's used to create the Spark context. That's going to be very cluster specific. That's why I'm not going to get into how you create. Now you say from the Spark context, load this text file, right? And by the way, this text file is sitting in HDFS, which is my distributed file system. And within that, there's a path to that particular movie file, right? And this is going to take this text file and it's going to create a RDD out of that. It's going to create a collection of items from this text file, where every row in this input text file will be one item in this RDD. To be a string, right? So what this does is that this file and creates a collection of strings, where each string is one cache. So ignore that for a minute. So things don't get affected much from a correctness perspective. You don't have, but from a performance perspective, it has an impact. So we'll come back to this. Now I'm trying to then perform what this return to me is a RDD, and I'm going to call that RDD variable, put it in the variable called m. Now I'm going to do m.map, and as I mentioned, when I do a map, I have to pass it a function, and this function is going to be applied on each item that's present in my input RDD, and the output from calling that function on an input item is going to be stored in the output RDD, right? So I have 10,000 items in my movies or m RDD. I will have 10,000 items in my mcalls RDD as well after I perform a map on that, right? And now let's see what's the function that I pass, right? This is an example of a lambda expression in Python, so you've got equivalents in other languages as well. So this is a way of sort of passing an inline function, right? So your function is an input parameter to map operator. says is that L is sort of, think of it as the input variable to your anonymous function, right? Which means that L is essentially a proxy for the item in the RDD that this function is going to be operating upon, right? Just like when you define your function signature, right? Essentially say sort of foo of int I, right? The programming will work exactly the same if you called it foo of int j. So I, j, all of these are just variable names. It's just a placeholder for something that will be passed through that function by your program. Likewise, when you say lambda L, it essentially says L is just a proxy variable name for each item in the input RDD, right? Which is each item in M, right? Now, what is it that you want to do with this input item? Now, I want to take L and I want to split it based on comma as a separator, right? So, the input is a CSV, which means you will have a line that has column 1, comma column 2, comma column 3, and so on, right? In this case, we have 3 columns. So, you will have movie ID, comma, movie title, comma, a list of genres. So, when I take this line and I want to split it based on a comma, and what this is going to return in this is all Python code, by the way. So, if I split a line using a comma, it's going to give me, it's going to take a string and return an array of strings. That's what Python does, right? So, the output RDD that's stored in M calls, the input M is a collection of strings. The output M calls will be a collection of string arrays, right? Because you've taken a single string, done a split, and gotten a string array out of that. And if the CSV file is properly formatted, each string array will have exactly 3 items, right? Because you got 3 columns over here. Now I'm going to take this M calls, string arrays, and now I'm going to just the okay, I'm going to skip for a moment the header row. Go through this 10,000 movies that are present. This file also contains a header row. The first row in this entire file is going to be a header row that just says movie ID, comma titles, comma genre. And the subsequent row is going to look like movie ID is like this, Toy Story is the name of the movie, title of the movie, and you got a list of genres that are separated by pipe symbol, right? Now, what I'm trying to do over here, unordered list. My RDD is an unordered list. There is no notion of the first row or the last row. So, I can't go in and say remove the first row because it's a header row. I have to actually write a transformation to do that. So, what I'm doing over here is I'm filtering, and I'm filtering out rows. I'm retaining rows such that the value of the third item in my 3-string array is not equal to genre. So, the only time it's going to be equal to the genre is for the header row. The header row would have been converted into an array of 3 items, and the third item in that would be called quote unquote genre, right? So, if I have a row where the third item is explicitly just called genre, that's probably a header row, drop it. If it is not that, then it's a valid row, right? I retain it, right? So, this filter is just going through the entire thing or operate on all the, right? So, this is sometimes the cost of working with big data platforms. You might have to do something, you might have to jump through hoops to do something very simple, just so that you get the guarantee of scaling to a large data, right? So, now this you have a list of movies present as a 3 item array, and the header row has been dropped off. That's what MG represents. It's an RDD with had 10,001 rows with the header row as one of them. This MG is going to have 10,000 rows with the header dropped off. Sorry about that. Now I actually want to go and the maximum number of genres that a particular movie has, right? So I'm going to go to the genre column again over here. So I'm going to do a map, and I'll take the genre column over here, and now I'm going to split it by the pipe symbol. So if you notice over here, you can have a list of genres and they are separated by the pipe symbol, right, or the mod symbol. So when you do a split like this, what this is going to return is a list of genres. And what's happening over here is something that's interesting. It's actually going to return number of genres that I have. It's going to return the length of the array that I have split into, which is effectively the number of genres that's in this particular, that's assigned to this particular movie, right? That's going to be the first part, right? But you actually see that you have this of the form A comma B. What this means is that your anonymous function that you're passing will return a pair of items, and Python is sort of fancy in this way. It allows you to do such things, right? So you'll call a function, and the function will actually return two parameters, two output parameters, right? It's not easy to do in things like Java and so on, right? And this is how it would look like, right? So if this were your input row, it would count, it would do the split based on a pipe over here and count this, which is, it's got 3 genres. So the output is going to look like 3, which comes, and then the second output parameter is L, which is the same as the input, right? Which means that I'm going to retain the original input as a second parameter, and I'll have the count of the genres as my first parameter. And this effectively you've created a pair of items, right? So we're actually trying to go from a simple line of text into a nested object, right? With semantic meaning that's present for this nested object, right? And this each object itself is an item in the entire RDD, right? Now the goal of this entire code over here is to figure out, give the list of movies which have the most number of genres assigned to them, right? That's sort of the overall goal, right? So now I've gone from the of the genres followed by the entire original row that was present. Now I call a max operator. Max again is a built-in operator, and as should be obvious, it's going to find the item which has the maximum value, right? In this case, if you got a pair of items, pair of values in your item, it's going to find the max of the first of those pair of items. First is going to find the largest value over here, which is going to be the movie that has the most number of genres. And if we got multiple movies with the same number of most number of genres, it's going to return one of those values, right? In this case, let's say 3 is the number of. Now you found out the most number of genres present in any movie. Now you have to figure out how to get those movies back, because you can have multiple movies with, let's say, 3 genres. Here you go ahead and do another transformation called lookup. So if you remember this MG count of the genres, comma, the original row that you have, right? When you go and do a lookup, the lookup is again going to happen on the first column of this item. So this will look up all movies with the genre count equal to 3. And that's going to be returned back to you, and that will give you the list of all movies having the most genres, right? The task might seem very simple, right? And if you actually wrote a Java or C++ or Python code, it might not be so complicated. It might not seem so complicated, right? But this is what you pay with having simple abstractions that are available to you. But you can compose applications from these simple, complex applications from these simple abstractions and have them scale dramatically, right? And have them weekly scale dramatically, okay? Any questions? I'll take a pause over here. And again, you'll be doing some of these things hands-on later on this afternoon, but I just want to make sure you get these high-level concepts okay. How many of you have done Spark programming before? PySpark, Spark, Java Spark. How many of you have done Python? Okay, not bad, most of the class. So So that means that you actually probably were able to follow on at least half of this, right? Just because you know Python, right? And this is not much different from how Python dictionaries or Python lists and so on work, right? So they would actually work in a fairly similar manner if you thought of each of these as Python objects, right? And you're just performing operations on top of them, right? So let's maybe jump to a couple of more categories of operations that you have. So we already saw how to. So we have a question over there.
Basically, I just wanted to know this Spark has a limited mechanism on the performance aspects. Like let's say I have this code snippet, I want to know like how much time it took and at what rate it is. Does it have inbuilt mechanism or libraries, or we should be having the time clock and
Right. So the question is, does Spark have built-in mechanisms for doing profiling of how long an application took to run, right? So what you're seeing over here is how you're writing this code as if it's a single machine code, right? Looking at this code, it's hard to even figure out that this is actually running on a distributed system, right? Because this looks like a simple code that you write on a single machine. Behind the scenes, what ends up happening, right? Every time you're performing an operation, this is going to go off to the cluster and perform this operation on all the machines holding the partitions of your RDD in this cluster, right? This code itself runs on, let's call a master, right? But every invocation to a transformation or an action is being done remotely, right? So there are two things that you'll have to measure. You can measure, let's say, you can put a sort of get time and sort of get time over here, subtract it, and you can print it. But that's actually going to include the time it took to, let's say, submit this job to the cluster. The job might wait in the queue to be completed and then come back, right? So it includes both the execution time and the queue waiting time, right? So that might not, it will be a wall clock time, it might not give you the actual execution time, right? For the individual operation. So for that, you will actually have to go into the logs for Spark, right? And I think that will be covered as part of your class as well. So that will actually sort of tell you for each of these operations, right? How long it was actually executing, how long it was waiting to be scheduled to acquire resources and so on before it starts executing, right? So that will give, then you'll have to sum it up to get the actual execution time, okay? All right, so this is this is one way of creating the text file. And I sort of told you I'd sort of deal with this cache later on, right? So,
sir, one question.
Yes.
So the previous slide which was showing, so it was like that the program is running on the master.
Yeah.
So when we say that the movies.csv file is huge, so now the first line which is actually converting into RDD,
Right.
so that action is happening only on one master.
That is happening remotely as well. So every piece of code that you see, everything in blue that you see over here, is causing a remote operation to happen, right? So that's one of the reasons why you're loading it from HDFS, right? So if you remember, we talked about HDFS itself being a distributed file system, which means this movies, it might be, let's say, a few hundred MBs in size, right? That might be split into, let's say, 10 MB chunks. And each of these 10 MBs, which might have a few hundred rows or whatever, might be present in a different machine, right? So when I do sc.text file, right? That's why this xc is actually getting a handle to a remote cluster, right? When you do sc.text file and pass the paths to an HDFS file, it's actually going to launch an operation that goes, fetches these blocks that correspond to movies.csv from HDFS into the memory of the machine on which those blocks are present. And all these blocks in memory, which are going to translate to partitions in memory for the RDD, collectively will look like a RDD. So RDD is nothing but it's a reference to a set of partitions sitting on remote machines. So the reference will be kept in this local machine, right? Which means when I look at this M, if I printed M, it'll actually tell me this M is actually a set of partitions and each partition is sitting on so-and-so machine.
So it means that converting the movies.csv file to an RDD is not happening by just one machine. I mean, there are multiple machines which are reading from this and putting it in memory.
That's correct. So it's going to be as many machines as are holding the blocks of movies.csv, right? It could very well be that movies.csv is a very small file. and it fits within 10 MB block. Let's say you had a 10 MB block, just for example, though it's much larger than that, right? So in that case, it's going to be a single machine that holds that block that will get loaded into memory, right? But that also means that you actually have only one partition, right? And one advantage of distributed system is only if you actually have more than one system. Otherwise, it's like a trivial operation, right? So if your data is too small, right? This is actually a caveat that I should have sort of disclosed right at the beginning. So before you start doing distributed programming, right? So make sure you need distributed programming, because distributed programming is costly. It is sometimes time consuming, both to code as well as to execute. So if you can make do with a program that runs on a single machine, right? In the memory of a single machine, or within the compute resources available on a single machine or a single thread or a single core, do that, right? Because running a Spark application to do what we did right now on a very small file is actually going to be much slower compared to writing an equivalent simple Python code that just loads that 10 MB file from a local file and runs it on a single machine, right? But if you want to scale, you need to do this, right? Other question? Yeah, sure. So Spark behind the scenes talks to the Yarn scheduler. I think it was there in the start. So the question was, does Spark have a load balancing mechanism, right? So Spark actually outsources its scheduling strategy typically to Yarn, right? But then there are two levels of scheduling. So one is acquiring a set of resources for a particular application. Like what we saw was a single application, right? A single data flow of the Spark, right? But once that is sort of allocated, there are different operations that you're performing. So those operations are going to be running within the resources allocated to it from Spark, right? And typically the way this happens is that Spark is going to try and run the transformation on where the partition is sitting, right? So let's say you ran this job, and you asked for 4 nodes from Yarn. Yarn gave you 4 nodes, right? So let's say each node can run one task, right? So when you, let's say, load this input file from this movies.csv into memory, let's say that input file had 10 blocks, right? So now you have 4 machines, right? So these 10 blocks would actually be spread across these 4 machines, right? Let's say sort of 3, 3, 3, 1, right? So because that's what the locality was, right? So now when you actually run something like a map, so what this map is going to do is the equivalent of running 10 jobs or 10 tasks, right? 1 per partition. And on each partition, a map task is going to run. And they will run as far as possible on the same machine where the partition is. It will try not to move that partition to a different machine, right? So it's sort of almost like an implicit job scheduling, because the compute or the task moves to where the partition is sitting, right? But then there are exceptions to that. There are some ways in which you can actually control that. You can actually say that you do things like a rebalance, where you can sort of go from, let's say, these 10 partitions. You can say do a rebalance or repartitions rather, right? And say repartition into 12, right? Because I have 4 nodes, I want it to be a multiple of 4. So that's where there's more load balancing. So that will actually take those 10 partitions and split it into 12. So this intelligence sits within the Spark job, like scheduler, task scheduler. Yeah. Right. So that's where there are 2 steps. So when you actually launch this job, and this is again something you will be doing in the afternoon session, you will actually specify, I need so many machines. So that at the coarse granularity, your application has access to how many machines you wanted, and that will be assigned to you by Yarn, right? So if Yarn doesn't have that many machines, your application will actually wait. But once it's been allocated to you, right, then it's a question of, we talked about this 3, 3, 3, 1, right? But at a time, only one of these tasks are going to be running on a machine, which means that you'll do 1, 1, 1, then 1, 1, you'll do 1, 1, 1, 1, then you'll do, once those are completed, you'll do 1, 1, 1, then 1, 1, 1, right? So that's the type of scheduling that happens. But here again, the 4th machine is being idle for 2 of the rounds, right? So that's where you can sort of either you can make Spark more smarter by having different kind of scheduling policies, by moving data to other machines, or you can explicitly from a user's perspective repartition it so that there's a bit more load balancing. Any other questions? Okay, let's move on a little bit. So again, you'll get the hands-on, that will be a little bit more interesting for many of you. Like I said, a transformation goes from one RDD as an input and generates another RDD as output. one of the ideas over here, so the second thing I'll reiterate, it's executing in a distributed manner, right? So every operation or every transformation that you're executing is actually running on a remote machine across all the partitions that are present for the RDD, right? This third part in terms of lazy evaluation, right? That's something that you have to be a little bit careful about, right? So because Spark tries to be a little bit smart about how the program executes, right? So though you're writing a program top down, right? And typically if you write a program, right, you've got a main method and you got a bunch of statements, you expect it to run from the first statement to the last statement, right? That's how most programs work. But Spark is designed for scenarios where you could resume from where you left off. Let's say you are running an application and halfway through it failed, right? So if you rerun that application and if it starts all the way from the beginning, you would have essentially wasted the computation that you had done earlier on, right? So what Spark tries to do is that it almost assumes that you're starting from a completed state, right? And then it says, okay, do I have the final output from my last line, right? So let's say it goes to the last line, you got the equivalent of an action there, which is like a return statement. Is a variable that I have in my return statement already available with value? If I already have it available, I'll just return it, right? But if not, it'll actually go to the previous line. So if this variable is not populated, what is the previous statement that will allow me to populate this variable? That's probably going to be another transformation. And the transformation will be present on an RDD, right? So effectively, if you look at this code, when you run this code, right? So this lookup is like a action over here. So if you look at the dependency graph, right? So all of this is just a dependency graph, right? So this max GCM depends on MGC and depends on applying this lookup operation on this MGC. MGC depends on applying this map on MG. MG depends on applying filter on mcalls. M depends on, right? So what Spark will try to do is that it will go to the last action, or let's say it will go to the action, right? It will actually go to the first action. So it will go to the action and say, is this MGC on which I'm performing the lookup already available? Let's say as part of you previously running this job, it terminating, and you having cached this or whatever, right? So if this already is present and already has value in it, complete value, it will directly call lookup. It won't even go over here, right? But if you're running this for the first time, obviously there's going to be nothing over here. It's going to be empty, right? So then it will say, okay, how do I create MGC? To create MGC, it will go back and see that, okay, to create MGC, I need to call map on MG. So it will check if MG is available in memory. It's already been computed. If you're running it for the first time, it's not going to be computed. So it will go back. It will try to sort of create MG and see if mcalls is available, mcalls is not available. So to create mcall and m is a dependency, it will see if m is available, m is not available. And then it will go and see how to create m. And then it says sc.text file. And that's sort of like the starting point. There's nothing before that, right? So it will actually now go and execute this. Once this is executed, m is going to be available, so it knows that it can actually start going. So it will actually go backwards first, trying to look for the nearest dependency that is satisfied. Start from there and then go forward, right? Do you guys sort of get that picture? Right? So it's like, look for the nearest answer, right? So if you're able to get an answer that's nearby, don't have to do it from first principles, right? Go to the closest variable that's already there, right? So this is fairly useful, but one of the sort of challenges with this is that if you don't put an action in your RDD, what's going to happen? There's nothing for you to do. Right? There's no action. So you'll go say, well, there's no action, nothing for me to do. So your program will complete really, really fast. Right? So the fastest Spark code you can write is something without an action. Right? So question in the back.
Yes. How does Spark do memory management and garbage collection?
Right. So Spark doesn't sort of, it actively manages the partitions that it holds in memory, right? So when a Spark application is allocated resources by Yarn, I talked about those 4 machines, right? That Yarn allocates it. Each of these 4 machines is effectively what it gets assigned as the equivalent of a container, right? Not your Docker container, but it's a Yarn container, right? And the Yarn container has a fixed amount of memory allocated, right? Let's say 16 GB of memory, right? So that 16 GB of memory is available to Spark, right? Now there are a bunch of Spark parameters, tuning parameters and so on, but loosely speaking, it tries to use no more than 85% of that, right? So you can use a certain fraction of that for holding on to your partitions, and a certain fraction of that will be available for the runtime state for performing your operations, right? So that's one part of it. The other part of it is that, let's say you have all these partitions, but you don't have enough memory to keep all the partitions, right? Let's say initially you loaded everything into memory, there was enough memory for your partitions. You created an RDD and that blew up in size. So you have 10 times more data right now. You don't have enough memory on your 4 machines, right? What Spark does, it's smart enough to actually push off some of these partitions to disk. Just like your virtual memory management in your OS manages memory pages, Spark internally manages its partitions, right? Because it knows more about the application than just delegating to the virtual memory manager of the operating system. So you can actually, it behind the scenes swaps out and swaps in these partitions from disk into memory, right? But you do have, as a developer, you do have some control over some of these memory management parameters, one of which is this cache. So when I put in the statement cache on an RDD, right, what it says is that it gives a hint to Spark, the Spark runtime, saying that this RDD is going to be used fairly often, right? So try to keep it in memory as far as possible, right? Because otherwise, the moment it's done with this particular, actually get garbage collected, the equivalent of garbage collected within Spark, right? So likewise, I can actually say that instead of a cache, I could actually say persist. And what that will say is that don't just rely on trying to keep it in memory, serialize it and keep it on disk, right? So that even if I run out of memory, right, or even if something fails, I can actually go back to disk, recover that RDD and start off from there. So you can actually give these hints to Spark in terms of memory management as well as persistence of your RDD to extend the longevity of your application. Other questions? Okay, let's try and go forward a little bit. So we have a few minutes and we'll see how far we can get to. Let me try a few other applications. So a few other transformations. So map is one of those. We talked about that. We use that also. Filter is another one. So sample, we talked about union. Sample is actually, it's actually fairly interesting operation that's unique to sort of these big data platforms, right? So you might have this big movie lens file with 10,000 movies, right? Or maybe 100,000 movies, I don't know. And you have this complex Spark application that you've written, and you go in and you execute it, right? And it sort of goes and does this text file, the spark.txt file, right? And it takes 3 minutes for the file to load from disk into memory, right? And then you run the first transformation, you get a failure, right? There was some bug in your code, right? Now you go back, fix your bug, rerun the application. 3 minutes waiting time for loading the disk, right? So this is actually going to be real. This is how you develop code, right? So you do it iteratively. You hit a bug, you sort of do it. But think about, you have to spend 3 minutes to load the data before every run, right? So that's going to be a lot of time penalty. So what Spark allows you to do, it gives a very shortcut for sampling a subset of data, right? So that way, you don't have to deal with the entire data, or you don't have to go through processing the entire data and then hit a sort of bug. Get a subset of the data, try out your code on that, right? If it's successful, just go comment off that line that says sample and run your code and you'll be running it. So this is a quick way of testing your code on a small subset of data. It's essentially randomly sampling. If you got 10,000 rows and you said that rdd.sample of 0.01, it'll give you 100 rows of that in random sample from the uniformly from across the different partitions, right? So this way you can quickly test your code before you scale it out, right? Union, we talked about it. Intersection is actually like a set intersection, unlike union, which is not like a set union, it's like a concatenation. Intersection actually does find duplicates or common items across two RDDs and only retains the common items and throws away the rest. Distinct again allows you to throw away duplicates and only retain distinct items. These are again like your aggregate operations in your SQL, right? Okay, so this is actually interesting. Let's see if I have a group by blah, 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 blah. Okay, let me try this reduce, right? So let's try one more example and we'll wrap up with this for this session, right? And that's essentially because all these sort of operators we saw so far are fairly straightforward. It is equivalent of iterating through all the items and doing some kind of an operation, a filter or a map or whatever on top of that. But one thing you haven't seen so far is reduce, and we started off talking about MapReduce, right? You've seen map. By the way, map that you saw, it is actually the map of MapReduce, right? So though I didn't mention that, right? So when Hadoop or Google came out with their MapReduce programming model, they only had two operations, map and reduce. Spark gives you a dozen more, right? So a lot more than just map and reduce, right? But behind the scenes, everything that you get from a filter or a join or everything can actually be represented just using map and reduce, right? It's just that the Spark compiler allows you to specify it in a more naturally fitting transformation, and behind the scenes compiles it to just map and reduce, right? But let's look at this reduce, because that's interesting. That's sort of the other piece that completes the puzzle. So reduce is something that takes a collection of items and it collapses that collection of items into a single item, right? And the idea is this. So over here you got lambda of a comma b. So what this means is that this reduce is going to operate almost in a hierarchical manner, right? Think of it in this way. Let's say all your items are the leaves of a tree, right? Are the leaves of a binary tree, to be more specific, right? But you don't know what's at the higher level, right? So when you do a reduce, what it does is that it takes two arbitrary items and calls, and they're assigned the variables, they're assigned to the variable a and b. And it applies this reduce function on top of those two items and replaces those two items with this one item, right? That effectively is your next level in your binary tree. And it does this for, let's say, all the leaves, right? Now you have n by 2 items. It does the same thing, right? Takes those n by 2 items, pair at a time, and creates n by 4 items, right? And so on. At the very end, you're going to be left with one item, right? And that item is effectively going to be whatever operation was done, it is going to be done pairwise. So in this case, it's a sum operation. It means that you take two arbitrary items, sum them up, and those two items are effectively replaced by this sum. And you keep doing this for all the items, and you go up the tree, all you're going to end up with is the sum of all the items in the entire list, right? Now, the nice thing about this is that you can do this in parallel for any two pairs on different machines, right? And in each machine, you sum up all the items as a tree, and then you sum across all the items, and you can get a single value, right? So those of you know merge sort, right? This is sort of a little bit like that. In merge sort, you start off with two sorted lists and you merge them together, right? And the nice thing about merge sort is that sorting of these two items can be done on two different machines. The merging can be done on a single machine. So the idea is similar over here. These individual operations, so the sort of can be done in parallel, and all of them can be cumulatively composed together to get a single item. So that's where you get the parallelization, right? All right, so that being said, actually one thing that's a little bit misleading is that this reduce in Spark is actually not the reduce in MapReduce, right? The reduce in MapReduce is actually called group by key or aggregate by key, right? And there the idea is that it allows you to do the equivalent of your group by in your SQL, right? In SQL, when you do a group by, right? What that does is that if you do a group by key, so all the rows having that particular key will be grouped together, right? And then whatever transformation that you pass or operation that you pass will be applied on each group separately, right? So that idea is fairly similar over here in, aggregate by key. So an aggregate by key requires a pair of values, right? We saw in the earlier example you had the count of the genres comma the line, right? That's an example of a pair of values. It's also called a paired RDD, right? It's got a key value pair. So when you do an aggregate by key, what it does is that it takes the key and all the keys that have the same sort of equivalence or same equal value, their corresponding value will get grouped together, right? So to give you an example, so if I did a map value, okay, let's do a reduce by key. In this particular case, this is your RDD. It's got, if I do a group by of this key, so all the rows having, which is their values sort of concatenated together, right? So I'll get the equivalent of 0, 1, the keys having pink concatenated or aggregated together, right? So 3, 1 and 4, 1 will be next to each other. Pirate is just a single, there's no other key called pirate, so that's going to have just a single value, right? So now what I'm doing over here is that I'm performing some kind of an operation. So all these values that I have as a list, I can perform some kind of a reduction operation, like a reduce, like a summing up of those values or so on, right? So this is sort of one of the more powerful constructs in, this is actually the construct from the reduce part of MapReduce, as well as there are various variants of this in Spark as well. But the idea is that given a key value pair, I can group by key and perform an aggregate operation on all the values that correspond to a single key, right? And that actually allows you to construct much more complicated applications, and that's something that hopefully Sriram should cover later on in this afternoon. So let me quickly see if there's something else interesting to talk about over here. Yep, that's pretty much it. Thank you.